Good morning. Hi, class. So the theme for today is friction, friction, friction. We're going to learn about friction. Before we get started, let's talk about the status of WebAssign. So there's a problem set due tonight, and I took a look at that, and you should be able to handle it if you're not finished already. All the problems on there are things that you can handle based on the topics we've covered so far. All right. So that's due tonight. I posted another problem set that's due next week, and it's a pretty long one. So don't wait till next week to get started on that. All right. It's more Newton's laws. It's called Homework 4, Newton's Laws, Part 2. All right, gang. So got fuzzy on my shoulder. So the topic of friction. Let's start by looking at a simulation and discussing what friction actually is. All right. So here's a simulation that comes from the PHYS website, and it's a simulation showing that when you have surfaces in contact, in this case, two textbooks, the surfaces in contact, at that point of contact, the materials touch. And materials are made out of atoms, molecules. And the zoomed in picture here, exaggerated to a great degree, is showing that the molecules that make up matter around us is constantly wiggling and jiggling. It's due to thermal energy, or I should say thermal energy is this microscopic wiggling and jiggling. And when two materials in contact rub against one another, you can do this with your hand, you rub your hands against one another, after a while, what do you feel? Heat. You feel the buildup of heat. So friction is a force that converts energy of motion into thermal energy. And the details of the energy part will be more clear later this semester. But for now, understand that friction is a force, and the force is there because you have surfaces in contact with one another and slide over one another. And microscopically, those surfaces are rough, and I can wiggle these back and forth. And you see that the thermal energy of the molecules increases because of this motion. I've worn away the chemistry book. So friction is due to this contact between molecules and surfaces in contact. All right, so let's switch to a different simulation now, okay? And this simulation is going to show that there's actually two kinds of friction, two types of friction that you could encounter in the physical world. All right, and so this simulation, here it is. There's a guy that can push on a box, and you can control. Let's look at the. So there's vectors on here for the forces. So if this guy pushes on the box, the box doesn't move. And the reason it doesn't move is, let's turn on the sum of forces. Excuse me, the box is, you're pushing on the box, but the box is experiencing friction. So there's two forces on the box. Let's turn up friction. There's this applied force that the dude is pushing to the left in this case, and there's a frictional force which is opposing that applied force. Okay, so the friction is happening down here at the point of contact between the box and the rough ground. Let's Move them over here. How do I move them over there? There we go. So now I'll push the other way. So I want you to pay attention to something. All right, so the lengths of the arrows here are communicating something about the strength of these forces. So you have this applied force and this frictional force that's opposing the applied force. So what I want you to pay attention to is, as I increase the magnitude of the applied force, how hard this simulated man is pushing on this crate. Watch what happens to the strength of the frictional force. Let's turn on the values. So the applied force is, when it's 50 newtons, the frictional force is 50 newtons. When the applied force is 80 newtons, the frictional force is 80 newtons. When the applied force is 120 newtons, the frictional force is 120 newtons. So you have this, there's a frictional force at work here, which is whatever it needs to be in order to balance the applied force. So you're pushing on the box in this direction, but friction is pushing back in the other direction. And importantly, the box doesn't move, it doesn't accelerate, because the two forces add to zero. The net force is zero. And it's only when you have net forces that aren't zero that you get accelerations. So I'm going to keep increasing the strength of the applied force, and there's going to be some point where this friction is no longer able to balance the applied force. And when that happens, you'll notice two things. All right, one thing is the crate will start to accelerate because now there's an unbalanced force. And the other thing will be that some other kind of friction takes over. And I want you to pay attention to the length of the arrow representing the strength of this friction. So at that moment when the crate starts moving. All right, here we go. Applied force is perfectly balanced by the frictional force, 150 newtons, 160, 180, 190. Okay, watch the red arrow right there. Let's do that again. Right around 190, 170, 180, 190, and almost there. And if I increase the applied force, the frictional force doesn't change now. Let go. Yeah, come back here. Okay. So what did you notice? What happened to the length of the arrow? The red arrow, the friction force. The instant it starts sliding. What'd you notice? I'm looking at your comments. I go for a jog a couple mornings each week, and this week it feels like winter. It's crazy. I'm wearing knit hat and gloves. The amount of newtons fell. That's right, Holly. So the moment that that crate starts moving, the amount of friction dropped, and then it stayed constant. Even if I pushed harder, it stayed constant. The amount of friction stayed constant. Okay. So what we have here is let's go to the. Oh, hold on. Helps if I turn it on. And there we go. Okay, so we'll go to the whiteboard on my Surface. And okay, so the topic of the day is friction. And the point of these video simulations are to show you that there are two kinds of friction. Let's call the first kind static friction. And our observations in the video, or sorry, in the simulation, our observations were that if I were to plot the applied force as a function of the friction force, what the video showed is that they're perfectly balanced, even as the applied force increases up to a point. Okay, there's a point where the applied force, here, so let me, static friction is red here. There's a point where the applied force is too great, and static friction can no longer compensate, can no longer oppose the force. And then what we saw is when that happens, there's another type of friction that takes over, and it's called let's call it kinetic friction. All right, and as Tyler noted in the, as Holly and Tyler noted in the comments, when kinetic friction takes over, its magnitude drops, but then it's constant thereafter. Okay, so as the applied force increases, you could have one or the other of these types of friction, and the force laws. Okay, so when I say force law, what I mean is the mathematical expression that describes the magnitude of these forces is different. Well, it's very similar, actually, but it's different in one important way. Get rid of that. And so I think maybe let's do kinetic friction first. So for kinetic friction, the formula for this type of friction, let's call it just F sub, I'm not sure what your textbook calls it. Let's do F sub FR for friction. The magnitude of this force of kinetic friction is equal to some constant, let's call it mu sub K for kinetic. Sometimes kinetic friction is called sliding friction, but then you have sliding S, static S. So let's stick with kinetic. There's some constant times F sub n, which is the normal force. Okay. So what I'm telling you here, and I could demonstrate that, you can demonstrate this to yourself, that the amount of friction there is between two sliding surfaces is a function of some parameter, mu, and that's something that is material dependent. Some materials like rubber have really high coefficients of friction, and some materials like ice or glass, smooth glass, have much lower coefficients of friction, it's a property of the material, and in the real world, this coefficient of friction, mu, would have to be experimentally determined. But the other factor is the normal force, and the normal force is this force of contact between two surfaces. And I can, if I have my hands like this, I can increase the normal force by pushing my hands together. Ooh. And now it's much harder to slide them because the amount of friction between my hands is increased. So the normal force is the force of contact between the two objects. Okay, so what about static friction? So if this is a force law, well, let's label this. This is coefficient of kinetic friction. So there's a table in your textbook showing the coefficients of kinetic friction for a bunch of common materials or actually, so it'd have to be like two materials, wood on wood, wood on glass. You can look up the coefficients of kinetic friction. Okay, so what about static friction? Well, it turns out that the force law for static friction is very similar, except there's a different coefficient, mu sub s, the coefficient of static friction. Do static friction. And the symbol between, so you think about this, all right. Let's see if you can figure this out. So I didn't put an equal sign there. And the reason I didn't put an equal sign there is because if you have a coefficient of static friction and you multiply by a normal force, that gives you a number. You know, for a given situation, there's some amount of friction. But our observation in the case, I mean, you can do this with your hand too. Apply a little force or a bigger force, you feel friction between your hands increasing or decreasing. And as I plotted it, the amount of friction, the amount of static friction between two surfaces increases with the applied force up to a maximum point. All right, so this number, this product of mu s, the coefficient of static friction, and the normal force, you think of that as the maximum amount of static friction that can be supplied in a given situation. It's a maximum amount. So in my picture here, this number right here would be the value of friction right there before the thing starts flying. It's the or sliding. It's the maximum amount of friction, static friction. So what symbol should I put between the left hand and the right hand side of this equation? The force of static friction is not equal to that. Well, it's only equal to that at one point. But for applied forces less than that maximum, the amount of friction is less than or equal to. Okay, so in practice, a lot of times, you know, you'll be doing a situation where you want to know some, you know, tolerance of a system, in which case, if there's friction, you'll plug in the maximum amount of static friction to kind of figure out your limits. We'll see that when we do a problem involving cars going around turns. Okay. So, all right. So two types of friction. Let's take a look at let's take a look at that incline problem that we did last week, except now it's a frictiony system. So there's friction between the object on the incline and the surface of the incline. Right? Okay. So we'll call this incline with friction. Okay, so let's start with, you know, a situation like this, where you have a crate. A lot of physics problems involve crates. That's so boring. There's a crate. It has some mass, m, and it's on this incline that's at some angle theta relative to the horizontal. Oh, come on. Okay. And there's some guy over here who's lifting up this end. And of course, when the incline is flat, the crate's not going to be moving. But at some angle, it's going to start sliding. It's going to start sliding down this incline. Need some color. Okay. And so the question here is, let's explore the physics of what's going on here, and let's find, or let's ask this question: does the angle when the crate starts sliding does that depend on the mass of the crate? Does it depend on the coefficient of static friction? So if we want to know something about when the crate begins to slide, that's a question about the maximum amount of static friction between this crate and the surface. And does the angle where the crate starts sliding depend on these things? What are some other things? Well, it could be g, the acceleration due to gravity, because that's pulling down the card. Well, let's proceed. All right. So we should always start. So this is a problem that involves forces. We should always start with a free body diagram. Okay. And so let's use F for force vectors. So we have a normal force. A normal force. We have a force of gravity. I'm going to call that Fg today instead of weight, or W. And then there's a frictional force. And so gravity, a component of gravity is going to want to pull this crate down the incline. So there's a frictional force that's going to oppose that tendency. And we'll use, so let's turn this into a more clean free body diagram. So here's our crate. Here's our normal, well, let's try that again. Here's our normal force. It's like exactly the same. Here's our force of gravity. And here is our friction. Oh gosh, why does this keep turning on? I'm struggling today with my pen. Wow, it's really bad. Let's try that again. Maybe if I draw from this side. There we go. So we have this frictional force. Okay, and let's define our coordinate axes like this, just like we did last time. So the direction along the normal force is the y direction, and the direction along the incline is the x direction. Okay. And what else we found last time is that if we extend the y-axis down through the normal force, the angle right here that axis makes with the force of gravity is equal to theta, the incline. All right. So, and then we proceed. You know, I can rotate my screen here. Unfortunately, it doesn't work for you guys. But you know, you can rotate everything, so that well, let's do it. How else could I draw this free body diagram? I could just rotate everything so the thing I called the y-axis is straight up. Right? Just rotate my axes. They're the same. I've just rotated everything a little bit that way. All right. Anyway, the way to proceed is we can use Newton's second law to write down a force equation in both dimensions. So let's do that. So smaller, and let's do the x direction first. So if I look at my picture here, the force of gravity has an x component and it has a y component. And using what I know about trigonometry, the x component of gravity is going to be the total force of gravity, which is weight, m times g, times the sine of the angle of incline, okay? And FGY is mg cosine of the angle of incline, okay? So we saw that last time. So in the x direction, in this case, the net force in the x direction is going to equal, there's a positive force, it's pointing in the positive x, it's the x component of gravity. And then there's a negative force pointing in the negative x direction, which is the frictional force. And Newton's second law says that total force, one's positive plus one that's negative, is equal to the mass of the crate times the acceleration in that dimension. Okay, so we can put those two things together. The force of gravity in the x. Here I'm going to be a little bit more explicit than I normally would. Let's write it out. So the net force, the sum of those two forces, Newton's second law says it equals mass times acceleration in that dimension. The x component of gravity is mg sine theta. And the force of friction, this is static friction because we want to know when it starts sliding. So the force of friction, let's go over here. In this case, the force of friction is less than or equal to the coefficient of static friction times the normal force. Well, we're interested where the crate starts sliding. So we're interested in the limits of friction. So we're going to ask what happens when that force of static friction reaches its maximum amount. So the force of friction is μs times the normal force. And that equals mass times acceleration in the x. Okay? So let me circle this equation. So that's what we get when we consider Newton's second law in the x direction. And come over here. What happens when we consider Newton's second law in the y direction? So in that dimension, the net force in the y direction equals one positive force pointing up, because I said up's positive, or in the positive y, the normal force, minus the y component of gravity. And Newton's second law says that that net force is equal to the mass of the crate times the rate of acceleration in that dimension. So put these two things together, normal force minus the force of gravity in the y direction equals mass times acceleration in the y direction. And the force of gravity in the y direction is the weight of the crate times cosine of the angle of incline. Okay. So in this problem, let me circle that, let me box that equation up. Okay, so applying Newton's second law to this situation, we get two equations, one for the x direction and one for the y direction. And if we look at this, what's common between the two? The normal force. You see that? The normal force, it's blue, is in both. So that's a tool or a fact that we can use to combine these two equations. So let's solve the equation in the y direction for f sub n. And oh well, this is pretty easy actually because it's sliding down the incline, not perpendicular to it. So just like last time, the acceleration in the y direction, the direction that's perpendicular to the incline, is 0. So that means the normal force is equal to mg cosine theta. And so we'll take that and plug it in over here, and we'll get, let's go down here, we get mg sine theta minus mu s, and the normal force is mg cosine theta, equals m times the rate of acceleration down the incline. And so one thing we find is that we could factor an m out of both sides. There's an m in every term, so it goes away. So exploring the physics of this situation, one thing we find is that, does the maximum angle of incline depend on m? Does theta, is theta a function of m? No, it's not. So let's solve this for theta. All right. So again, at some angle of incline, the crate is going to start sliding, and we can figure. And actually, if we solve for theta in this problem, we find that angle, because when we approached this problem, when we pursued this problem, we said we used an expression for the maximum amount of static friction. This guy over here. So if we use this formula and plug it into these expressions and solve for theta, that tells us the maximum angle that this incline can be before the crate starts to slide. So let's solve this for theta. Oh boy. Maybe I will all right, I know what I'm going to do. So the thing that I don't know, I had a little brain hiccup there. So I was looking at this and I was like, you have if I want to solve this for theta, what should I do? And I was like, well, I got two terms with theta, and how could I combine them? I mean, you just can't factor out a sine or a cosine. But what you can do is rearrange this in terms of the tangent function, since tangent is sine over cosine. All right. So back to work here. All right. The other thing we know about this is we're considering a situation where the crate is not sliding. We want to know the maximum angle before it starts sliding. So if it's not moving, the acceleration in the x direction is 0 as well. Okay? So that means this whole expression g sine theta minus mu s g cosine theta equals 0. Okay? And so let's add the mu s g cosine theta to both sides. That gives us g sine theta equals mu s g cosine theta. And what do we notice here? There's a g on both sides. So we could divide that out and it goes away. And now we answered another question. Does the maximum angle of incline depend on g? Is it a function of g? No. So the answer we get is not a function of which planet you're on. The maximum angle of incline for a given ramp for sliding before the incline before it starts to slide would be the same on the Earth as it is on the Moon. The answer doesn't depend on which planet you're on. All right. Then let's divide both sides by cosine theta. getting smaller and writing bigger. So we have sine of theta divided by the cosine of theta equals the coefficient of friction. Sine over cosine is tangent of theta. Wow, this is really simplified a lot. And so if I want to solve for theta, I just take the inverse tangent of both sides. So the inverse tangent of the coefficient of static friction equals the maximum angle of incline before things start sliding. Max angle. Okay. Zoom in on that response, those two equations. Okay, so what we find is the answer to this problem doesn't depend on the answer here doesn't depend on g. It doesn't depend on the acceleration due to gravity. So this physics is planet independent. Doesn't depend on the planet. There's got to be some gravity, and you think, well, why might that be? And the reason is because you had two forces in this problem that depend on the strength of gravity. There was the weight of the crate, okay, which tends to pull it down the incline, but the normal force as well depends on the force of gravity. It depends on the weight of the object, and that opposes in the other direction. So if you increase one of these forces, the other force increases in exactly the same way. So they are always balancing out in exactly the same way. The mass of the crate doesn't matter, and that's because of the similar physics going on here. The mass influences the weight influences the normal force, so the mass increasing would increase both the component of gravity pulling the thing down the incline and the frictional force trying to oppose that. Okay, so it's likely you might have to review this problem before before it starts to make sense to you. It's there's a lot of new stuff in here. All right, it is 9:48. So we're not going to get to turns today, but let's take a look at another incline problem. Okay, so once the thing starts to slide, now you no longer have static friction. Now you have kinetic friction. And it's an interesting observation that the magnitude of kinetic friction is less than the maximum amount of static friction. You have probably experienced this. If you've ever pushed a car that was broken down, or tried to move a piece of furniture across the floor by pushing on it, the experience that you had was probably something like this. You have to push really, really hard to get that thing started, but then once it's moving, you don't have to push quite as hard to keep it moving. And that reflects this phenomenon of the sliding friction is always less than the maximum amount of the kinetic friction is always less than the maximum amount of static friction. So once you overcome the opposition of static friction, the amount of kinetic friction, sliding friction that you need to overcome to keep that object moving is less. It drops off. So we saw that in the simulation with the magnitude of that force dropping. All right, so most of you have had an experience like that at some point in your lives. Okay, So let's do a scenario like this. You have a sliding board. Sliding board. And there's a kid on here. It's gotta be a kid because, you know, adults don't use sliding boards. Whee! Going down the sliding board. And the sliding board has an angle of incline. The kid has a mass. Just like the last picture, there's a normal force that's supporting the kid on the sliding board perpendicular to that to the incline. There's a force of gravity, and there's a frictional force. Alright, so if I draw a free body diagram, there's the kid. At some point you can probably skip this step because, you know, what we have over here is basically a free body diagram. It's just got more detail in it than it needs to have. So I have a dot which represents the kid, and then there's the normal force, there's gravity, there's the frictional force, and I'll have coordinate axes that look like this. Positive x goes down the incline, positive y is perpendicular to the incline, and just like the last problem, that means that angle that gravity makes with the y-axis, the thing I called the y-axis, is the angle of incline. So gravity has an x component, which is equal to the force of gravity, the weight, times the sine. Try that again. Force of gravity in the x direction equals the weight. Why don't we just do this? Skip a step. Weight is mass times g. So that's mg sine theta. And the force of gravity in the y direction equals mg cosine theta. Alright, and so now I can write out, let's write out Newton's second law for the y dimension. The net force in the y direction equals the normal force, which points up the y-axis, minus the y component of gravity, which points down the y-axis, and Newton's second law says that's equal to the mass of the child times the rate of acceleration in that dimension. And the child isn't accelerating perpendicular to the slide, so that's 0, which means just like the last two problems, the normal force is equal to the y component of gravity, mg cosine theta. In the x direction, you have the net force in that direction is equal to a positive force, which is the x component of the child's weight, gravity, mg sine theta, minus the frictional force, which in this case is kinetic friction, equal to a coefficient of kinetic friction times the normal force. That's the force of kinetic friction. And that equals the mass of the child times its rate of acceleration. Okay, so just like before, the thing that connects the two dimensions here is the normal force. So I can plug that in down here and get an equation that looks like this. Mg sine theta minus uk mg cosine theta equals m/ax. And just like before, every one of these terms has an m in it, which cancels. And on the right hand side, I could factor out a g. sorry, the left-hand side, I can factor out a g. So I get this equation that looks like this. And so we think about the physics of this a little bit. All right, so one thing we see is that in the case of sliding, all right, so we're going to look at this equation and see what factors of physics influence the motion here. One thing we see is that the acceleration of the child down the slide doesn't depend on the child's mass. Doesn't depend on the child's mass at all. So, this means the sliding board works the same regardless of who's using it. In the real world, well, let's look at the other parameters here. So there's a acceleration due to gravity. So when the child is sliding, the rate of acceleration depends on the acceleration due to gravity. So unlike the previous example, a child on the sliding board on Earth, all things equal, would accelerate faster than that same child on the moon or on Mars, where g is less. The acceleration depends on the angle of incline. Theta's in there. And there's also this term which depends on the coefficient of static friction. Sorry, the coefficient of kinetic friction, sliding friction. And so that tells us that the material that the slide is made out of matters. Is the slide a metal slide? Don't see many of those anymore. Or is it plastic? Which of those materials would probably have a higher coefficient of static friction? It also depends on what the kid is wearing. Is the kid wearing jeans? Is the kid wearing like sweatpants? Is the kid wearing nylon shorts? Is that kid's skin exposed and getting stuck on the slide as he or she tries to slide? All those things will influence mu, the coefficient of static friction. Okay, so we covered a lot today. Let me go back to Chrome. Let's finish up here by going to so it turns out, Holly, I don't need another pen. Check this out. So here's my new pen. And the top unscrews and it got loose. And that was affecting how it works. All better. Hopefully the skin isn't exposed to the metal slide. Ouch. Yeah, a lot of us have had that experience. Or on a bright sunny day, the hot metal slide. So there's a shoot problem here. You should be able to do this problem now. Let's go to the book though. What I'm looking for here is, here's an explanation of friction, static friction versus kinetic friction. That should look familiar to what we saw today. Here it is. Okay. So there's a table. All right, so one of your problems involves it says, somebody is pushing a cylinder into a piston, or I can't remember how it's termed, but it's basically you're taking two pieces of metal and pushing one cylinder into another, and the first part of the problem in the homework says the cylinders are dry, which means you're sliding metal on top of metal. And you can look at this table to figure out what the coefficient of friction, of sliding friction, of kinetic friction is between, and the coefficient of static friction is between metal and metal. All right, so there it is, steel on steel. The coefficient of static friction is 0.6. The coefficient of kinetic friction is 0.3. You go down this table, you see that pattern. The coefficients of kinetic friction are always less than the coefficients of static friction. Well, less than or equal to. Teflon apparently is the same. And that reflects the fact that the magnitude of kinetic friction is always less than the magnitude of the maximum amount of static friction. And then in the second part of that problem, it says, well, how much easier would it be to press this metal cylinder into this other metal cylinder if you have oil, if there's oil on the materials. And to do that problem, you just look at the table, and now you have a different coefficient of friction. Look how much less they are. It's a factor of 10 less, over a factor of 10 less. Okay, so I just want to remind you that use your textbook to review this material, but also there's information in there that's helpful for working on some of these problems. All right, bone lubricated by synovial fluid. Oh, man, I feel like, I say I go for jogs some morning. I'm getting so old. I got like creaky joints and sore muscles. It used to be a time when I could run 5 miles and then get up the next day and do it again. And now I run a mile and I got to take a day off. Man, getting old is not, it's not fun. Well, it's not all bad either. There's good things about every point in your life. My high school biology teacher told me that once. He said, someone asked, was high school the best part of your life? And she said, it was pretty good, but college was really good too. And then after college, that was really good too. And getting married and having kids, that was great too. Every part of your life is great. Different, but every part of your life is great. All right, I digress. I will see you guys on Friday. Okay, sign up. I'll be in there in Bird 110, and I'm looking to do another web tutorial video as well. So I'll post that sometime this week. All right, take care. Talk to you later.